So today's topic will be about finding the divergence of a given vector field using the div operator, also known as nabla dot. Now, what this operator acts on is a vector field. Let's say f1xy, f2xy as an example, and it turns it into a scalar field, or what is a better definition of it, like a way to find out how much arrows are falling into a specific place at one time or going away from a specific place at one time. And the way we do that is we find the partial derivative of f1 with respect to x, and then we add it to the partial derivative of f2 with respect to y. Now, when we do this and we derive the divergence, we can input x and y and find out whether the divergence at a point is positive or negative. Positive divergence means that the arrows are escaping from the point, while negative means that they fall into a point. This is very useful for understanding things like fluid dynamics, or maybe even the way wind moves. So, let's take an example of positive divergence. Let's say we have vector field x, y. Now, this is also known as xi plus yj. This needs to be put on a 2D plane because the output space is two-dimensional. So how do we graph this? Well, let's go to 1, 0, and we see that it's going to be a straight line in this way. 1, 1 is going to be like this. So the points are all diverging away from the origin. So let's calculate the divergence of this. We're going to do the partial derivative of, let's say, this function, which is f of x, and this is f of y. We're going to do the partial derivative of f with respect to x plus the partial derivative of f with respect to y. Let's do f1 for the sake of notation. So, when we do this, the partial derivative of f with respect to x yields 1, and the partial derivative of y, of f1 with respect to y also yields 1. And we will see the final solution is going to be 2. So we have a divergence of 2 for the vector field of x, y. And due to the fact we got constants, the divergence is equal all throughout the vector field. Now, how about an example with negative convergence? Let's say we have vector field minus x minus y. Now, let's do the same thing. We take the partial derivative of, let's say this is f of x and this is f1 of y. We take the partial derivative of f with respect to x and add it to the partial derivative of f1 with respect to y. Now, when we do this, it's going to be minus 1 plus minus 1, which yields minus 2, meaning that there is a convergence of minus 2 all throughout the field. So, let's go on to a more difficult, or because the topic's simple, a more times expensive problem. Now, sine x, y and cosine y x as the vector field. So this is f of xy, let's say, and this is f1 of xy. We're going to add the partial derivative of f with respect to x to the partial derivative of f1 with respect to y. Now the partial derivative of f with respect to x for sine x y is going to be cosine x y. So we're going to get cosine x y. And let's specifically find the divergence at x is equal to 90. And let's use degrees in this case because I'm more comfortable with degrees than radians for some reason. So let's add this to the partial derivative of f1 with respect to y. And that's going to be equal to minus sine y x. So we're going to get minus sine y x, and let's also specify that y is equal to 90. Or let's just keep it at 0 degrees. Of course, I'm only using degrees to notify you guys because degrees don't belong on any coordinate plane. So, in this case, we automatically assume that this is going to be 0. And sine of 0 is equal to 0 as well. So this is also going to be equal to 0. So we have 0 divergence. Thus we have no divergence or convergence at this place. Hope